Let us move on to tutorial number 9. This is on stoichiometry. This is a theory where we will try to calculate the amount of oxidizer required to burn 1 kg of fuel or 1 kilomole of fuel, assuming that complete combustion takes place. Okay. So, theoretical amount of air which is required is calculated using this study. Problem number 1. Ethanol, ethyl alcohol is burnt in a furnace with an equal ratio of 1.1. If no hydrogen or oxygen is found in the exhaust, determine the product composition. Okay, now equivalence ratio is given as 1.1. Okay, so that means the amount of air supplied is basically less than the required theoretical amount. Okay, so let us do this problem. First, let us write the equation, chemical equation, plus, so I will write first the stoichiometric equation, that is assuming complete combustion. Okay, this O2 plus 3.76 N2. So this is nothing but the air, standard air, which contains 0.21 O2 and 0.79 is the mole fractions of O2 and N2. So that is what is given here. I'll say A times of this will give you all the C converts to CO2, all the H converts to H2O. Okay, now that will be 2 CO2 plus 3 H2O plus all the nitrogen remains inert, that is 3.76 A into N2. Okay, now this is the complete combustion where all the C converts to CO2, all the H converts to H2O and nitrogen remains inert. Okay, so now this is the stoichiometric, that means the actual theoretical amount of air which is required to completely burn 1 kilomole of the fuel is considered. So by balance, balance of the C balance, H balance, etc. I can do. So what is C balance? In the left hand side, 2 atoms of C is there. In the right hand side, I get 2. That is the balance. Similarly, H balance, you can easily see that in the left hand side, 6 atoms of hydrogen. And right hand side also is 3 into 2, 6. That is it. So now you give O balance, you will see that 2 into A. In the right hand side, I will have the atoms, O atoms. So in the right hand side, 2 into 2, 4 plus 3. But in the left hand side, 2O is in the oxygen side, but in the fuel there is 1O. So I have to take 1 plus. Correct, 1 plus 2A. 1 in the fuel itself plus 2 into A in the oxidizer. But in the right hand side, I have 4 O atoms in CO2 and 3 O atoms in this. So this implies A will be equal to 4 plus 3 minus 1 divided by 2, which is equal to 3. So the stoichiometric equation can be written as 3 times O2 plus 3.76 N2 giving 2 CO2 plus 3 H2O plus 11.28 N2. But now in the problem, phi is given as 1.1. What is phi? Is defined as air fuel ratio stoichiometric divided by air fuel ratio actual. Okay, so now what is air fuel ratio stoichiometric? That will be the mass of air. Any air fuel ratio is defined on the mass ratio. Mass of air divided by is actually mass of air divided by mass of fuel. So that can be calculated as, here in this case it is 4.76 A into number of moles into molecular weight, that is 20 8.84, let us say, for the air, divided by molecular weight of ethanol, that is 12 into 2 plus 6 plus 16. Okay, so that will be 24 plus 6, 30 plus 16, 46. So that will be the stoichiometric divided by actual air fuel ratio, that will be 4.76. So here A is known, I'll just put 3 itself here into 3. Here I don't know, so I'll just put A here into 28.84 divided by 46. So this is given as 1.1. So from that I can write the equation now as 3 by 1.1 into O2 plus 3.76 N2. Now please understand, I have to supply at least 3 moles of O2 to completely burn 1 mole of ethanol. But now I am supplying less amount of air, that is 3 by 1.1 is less than 3. Okay, that means I will convert only some amount of C to CO2, some amount will remain as CO itself. So, but in the problem it is given that no hydrogen or oxygen is found. Obviously, oxygen will not be found because it is rich. Maybe if temperature is very high, dissociation can occur, then oxygen can be there, but that is also ruled out here. So, hydrogen and oxygen are not found. That means all the hydrogen has converted into H2O. Okay, so that I can easily write. First I will write H2O 3 times, that is there in the product. Now CO2, if everything is converted, it will be 2, but it is not converted, so I will say A times CO2 is there, plus since oxygen is limited, I will say B times CO also is there, plus nitrogen says inert, that is 3 by 1.1 into 3.76 times N2 will be there. So now I can calculate A and B by balances, correct? So that will be by carbon balance, I will say 2 equal to A plus B. Then by O balance, I will say here 1 plus here 3 into 2 by 1.1. That will be equal to this side, this is 2 times A plus B. So there are 2 equations, 2 unknowns. Solving, I will get A equal to 1.4546 and B equal to 0.5454. So that means the products now can be written as 3 times H2O plus 1.4546 CO2 plus 0.5454 CO plus 10.2545 N2. So that is the thing. So we are supplying less amount of air than the stoichiometric value. So hydrogen takes immediately the required amount of oxygen, but C doesn't convert as quickly as hydrogen, so some CO remains in the product. Now the second problem, in a combustion process with N-decane, C10H22 and air, the dry product mole fractions from products are formed, and obviously since hydrogen is there in the hydrocarbon, so hydrogen is there in the fuel, water vapor will be produced, but as a mixture of the hot gases and water vapor goes through, when we have to analyze it, it should be first cooled. Normally when you cool it, the water vapor will condense, the liquid water is removed, and the dry product gases will move through the analyzer, and analysis is done. Here it's a volumetric analysis, so we got the mole fractions. So products basically are nitrogen, some oxygen also is seen, CO2 and CO is also there. Obviously H2O will also be there, but it is not known to us because it is removed and the analysis is carried on. Now with this product information on dry basis, Find the equivalence ratio, percent theoretical air of the reactants, molecular weight of the products, and mole fraction of CO2. That's what we have to find. So, solution. Okay, I know that. So, if you add these fractions, it will come to 100. So, for producing 100 kilomole of dry products, 100 kilomole of dry products, okay, let us say let x kilomole of fuel is burnt. Okay, so now we can write the equation as x times C10 H22 plus, I don't know the amount of air, so I will say A times O2 plus 3.76 N2 giving, obviously H will convert into H2O, so I have to write some B times H2O, which I don't know, I will determine that, plus now all the fractions of other thing I will put percentage into number of moles itself, because I am saying that 100 kilomole is of dry products are formed. So that means if I say CO2, I can write 10.56 kilomoles of CO2 plus 0.92 kilomoles of CO plus 4.91 kilomoles of O2 plus 83.6 kilomoles of N2. So this will be the thing. I am put X here because if X kilomoles of, I am assuming that X kilomoles of decane is burned to form 100 kilomoles of dry products, and obviously the H2 also is included in the reaction. So now how will I solve this? By doing the balances. So I will say N balance first. N balance 3.76 A will be equal to 83.61. So N2 balance, let us say N2 balance. So that I will give A as 22.2367. That A is got. Correct. Now I will say C balance. That means here 10 into X equal to right hand side 10.56 plus 0.92. That implies I can solve for X, which is equal to 1.148. Then H balance, H 22 into X, 22X equal to B into 2, correct, 2B. So that means X I know 1.148, so I can solve for B, which is 12.628. Okay, now I go to, so now all are known, but this equation is written for X kilomoles, that is 1.148 kilomoles of decane. Let us divide this now by X and write the equation as usual for 1 kilomole of fuel. So that means A has to be divided with this 1.148. So I can say it is 19.37 times O2 plus 3.76 N2, giving B is actually 12.628, but that is divided by 1.148. So I can say it is 11 times H2O. So obviously 22 atoms will produce 11 molecules of H2O, plus I can write to other species 9.98 1986 into CO2, mole of CO2 plus 0.801 CO plus 4.277 O2 plus 72.83 N2. That is the equation. So now this is the actual amount of air supplied. Basically, if you want to write the stoichiometric equation for this value here can be written as 10 plus 22 by 4 for stoichiometric. Okay, but now we can see this is a difference. So let us say first I will find the actual air fuel ratio, that will be equal to 19.37 times 4.76 into molecular weight of air is taken as 28.84 divided by the molecular weight of this, that is 10 into 12 plus 22. So that will be 18.726 kg air per kg fuel. That's the actual air fuel ratio. Now stoichiometric air fuel ratio we will find. Stoichiometric air fuel ratio, that will be, as I told, 10 plus 22 by 4 will be the A value into 4.76 into 28.84 divided by 142. So that will be equal to 14.985. So what is equivalence ratio? Equivalence ratio is equal to air fuel ratio stoichiometric divided by air fuel ratio actual, that is equal to 14.985 divided by 18.726 equal to 0.8, that is more air is supplied than the required amount of, or the theoretical amount of air. Percentage theoretical air will be equal to 100 by phi, which is equal to 125%. That is 20%, 120% of air is supplied than this compared to stoichiometric. So now finally it is, what is asked is molecular weight of the products. Molecular weight of products and the mole fraction of CO2. So what is the total number of moles in products? Products is 98.1 moles. So go back to this equation. In this equation, if you add this 11 plus 9.1986 plus 0.801 plus 4.277 plus 72.83. So that is the total number of moles, that is 98.1. Then I want mole fraction of CO2. So number of moles of CO2 is 9.1986. So mole fraction of CO2 will be equal to 9.1986 divided by 98.1, which will be equal to 0.09376. So molecular weight of products now will be sigma xi molecular weight of I. So you know the number of moles. So this can be written as 1 by n total, which we have calculated, n total products into sigma ni molecular weight of I. So the number of moles you can see here. So 11 into 18, 9.1986 into 44. Like that, if you substitute, then you will get the value as 28.555 kg per kilomole. So that is the value. So you can see that only by knowing the product information on dry basis, we can calculate how much air has been supplied and so on. Okay, here the analysis will be accurate enough to capture the species like CO2, even CO and OH, etc. so that we will get accurate values of this. So we'll move on to the third problem. You have typical fuel gas mixture as the following volumetric analysis: 10% CO, 45% H2, 35% CH4, 4% C2H2, 2% O2, 2% N2 and 2% CO2. So basically, if you gasify any solid fuel or a very heavy liquid fuel, you get some gases out of that. typical composition is given. Okay, so this is by volume, and you can see that here the fuel components are COH2, CH4, C2H2, and some amount of oxygen and inert species like N2, CO2 are also present. Now, when I want to burn this gas mixture, fuel gas mixture, I want to know what is the amount of air to be supplied. So, stoichiometric air fuel ratio to be determined, plus if this is burned to 20% excess air, what will be the product composition, that also I want to know. This is the third problem. So, let us say I will this, if you add up 10, 45 etc., if you add up, you will get around 100%. So, now let us say my fuel stream or a fuel will be written as 0.1 CO plus 0.45 H2 plus 0.35 CH4 plus 0.04 times C2 H2 plus 0.02 times O2 plus N2 plus CO2. This is the fuel. Plus I add air, O2 plus 3.76 N2. I don't know what is the total number of moles required, A. But the products again, all the C converts into CO2. Okay, because of stoichiometry. This is stoichiometric, that theoretical. So I will say B times H2O. All hydrogens converted into H2O plus C times CO2 is formed. But please see that there is another some amount of CO2 in the fuel itself. So we will assume that nitrogen and CO2 will just come out and be inert. So that means I can write CO2 here as C plus in the products, in the reactant side 0.02, that amount of CO2. Similarly, nitrogen 3.76 times A comes in the oxidation stream, but in the fuel stream 0.02 is present. That's all. So no other thing is present, completely combust. Now please see, some oxygen also is there. So the A value what you calculate should exclude this available oxygen already in the fuel stream or fuel. So this is the stoichiometric this. Again, I can calculate the unknowns A, B, C, etc. by using the balances of atoms. So let us do the carbon balance. Left hand side 0.1 in CO plus 0.35 plus 2 into 0.04 plus 0.02 in this CO2 there. That's the left hand side. The right hand side, again this again goes to the right hand side. So C plus 0.02. That's all. So no other carbon. So this implies the unknown here is C, which is equal to 0.53. Now do the H balance. Left hand side, hydrogen 0.45. 0.45 into 2 plus here 0.35 into 4 plus 0.04 into 2 here, then that's it. The right hand side I have H2O here only, so 2 times B, which implies B will be equal to 1.19. Now O balance. O balance, left hand side 0.1 plus here 0.02 into 2. Correct. Now in the right hand plus here the oxidation stream plus 2A, that will be equal to the right hand side B plus 2 times C plus 0.02. So that is the equation. Now C I know 0.53. Okay. Similarly B I know 1.19. So I can calculate A. So A will be equal to 1.075. So that means I can write the stoichiometric reaction now as 0.1 CO plus 0.45 H2 plus 0.35 CH4 plus 0.04 C2 H2 plus 0.02 O2 plus N2 plus CO2 plus A is 1.075 into O2 plus 3.76 N2 giving 1.19 H2O plus 0.55 CO2 plus 4.062 N2. That is the equation. Now, what is the stoichiometric air fuel ratio? So, now we have to find the mass of fuel, molecular weight of fuel. Molecular weight of fuel I have to find. I know the mole fractions and the components. So, do this sigma xi molecular weight of each component. That may be got as 0.1 into 28, CO is 28 plus 0.45 into 2 plus 0.35 into 16 plus 0.45 into 26 plus 0.02 into 32 plus 28 plus 44. So that will be equal to 12.42 kg per kilomole molecular weight of fuel. Okay. That means I can say air fuel ratio stoichiometric will be equal to 1.075. That is A into 4.76 into molecular weight of air is 28.84 divided by 1 mole of fuel which has molecular weight of 12.42. So it's 11.882 kg per kg fuel, the kg air. That is this. Now when
கீழே வந்து அந்த 0.4 into 26 அது வந்து 0.04 into 26.
okay, so this will be actually 0.04 into 26. Okay. So when the fuel mixture is burnt with 20% excess air, that means I will write the equation as I want to find the product. So 0.1 CO plus 0.45 H2 plus 0.35 CH4 plus 0.04 C2H2 plus 0.02 into O2 plus N2 plus CO2 giving a plus air. Now 20% excess is added, so I will multiply the A as 1. A with 1.2, that is 1.075 into 1.2 times O2 plus 3.76 N2. Now products obviously 1.19 H2O. Air is excess, so the excess nitrogen and oxygen will appear in the products. plus 0.55 CO2, no changes here, but you will see the excess oxygen is supplied comes out as O2 in the product, and the number of moles for nitrogen has increased slightly because of the excess air is coming in. So this is the product stream or the product composition. This is about this. So when the mixture is there, we have to take into account of the O. See, the mixture, fuel mixture, there may be some O2, there may be some N2, etc., or some products also like CO2 will be present. Because this is because of the devolatilization or gasification of some solid fuel. So such a mixture comes out, but still it has good calorific value. So we can burn it, but the air calculation should be properly done accounting for the oxygen content in the fuel, inerts contents, etc.